All right, so we're going to be talking about our third colligative property today, freezing point depression. Remember before we were talking about three total. We did vapor pressure lowering, boiling point elevation, and today we're going to do freezing point depression. And we're going to learn how to calculate that depression. So just to kind of refresh your memory, we had to first be able to figure out what the Van't Hoff factor is for each type of solute. And one of our first ones we did was a covalent compound. And remember, covalent compounds don't produce ions in solution, so they won't break apart. So our CO2 will remain as CO2, so you only get a Van't Hoff factor of 1. So covalent compounds, 1. KBr, potassium bromide, I think we're getting comfortable understanding that that will break apart into 1 potassium and 1 bromide for a total of 2 ions, so a Van't Hoff factor of 2. Ammonium phosphate, lots of letters and numbers there, but just recognize the ammonium NH4. There's 3 of those and 1 PO4 phosphate. Total of 4 ions when it breaks apart, so a Van't Hoff factor of 4. And then sodium hydroxide, that will have a Van't Hoff factor of only 2, not 3. The hydroxide stays bonded as a single ion. So producing those numbers will be key for getting the freezing point depression correct. All right, so let's talk about freezing point depression. Essentially, if you dissolve a solute into a solvent like water, water will no longer freeze at 0. It'll freeze below 0. Why? That is the best question ever. Why do things happen? Well, essentially what's going on is that solute is disrupting the intermolecular forces of the solvent. And remember, water, its IMF is hydrogen bonding, and it makes it form that beautiful hexagonal structure. Well, it can't form the hexagon, and it can't form those hydrogen bonds in a solid ice if the solute gets in the way. So essentially what happens is the solutes get in the way, and so you have to take away a lot more energy to get the water molecules to organize in any sort of way. Our freezing point depression equation is very similar to boiling point elevation. The only difference is you have an F instead of a B. So delta TF means the change in the freezing point temperature. IKFM. So again, delta TF is the change in freezing point. I is the Van't Hoff factor. K is your molal freezing point constant, which we get off the table. And M is molality. Remember, that's moles divided by kilograms of solvent. All right, before we move into a problem, just refresh your memory. We have tables, various tables. In this case, we have a table with different solvents, but we're going to be focusing on water again. And we're going to look at our KF because we want the molal freezing point. And so we're going to be looking at that 1.86 number. That's our tabulated number. Okie dokie, let's go ahead and do a problem. What is the freezing point depression of water in a solution of 17.1 grams of sucrose? And they give us C12H22O11 in 200 grams of water. And what is the actual freezing point of the solution? All right, lots of words in there and some numbers and symbols. Let's go ahead and pull out some information. And we want to make sure that we can solve for this equation. So, 3 things I can get right off the bat. The mass of the sucrose is 17.1. The mass of the water is 200 grams. And I, the Van't Hoff factor, is 1. Why? Well, when I look at that C12H22O11, that's a covalent compound. It's a sugar. It is not going to break apart. So it stays a single molecule. I is 1. Some other stuff I can get, which is not given in the problem necessarily, but we just looked at it on the table. KF is 1.86 degrees Celsius per molal, and molar mass of sucrose is 342.30 just by adding up all those carbons, hydrogens, and oxygens. All right, first steps first. Well, to calculate delta TF, we need the molality. Well, molality is moles divided by kilograms. So our first step is to figure out moles. Remember, if you don't know what to do, always go to moles. That will help guide you. So here we go. We're going to take the 17.1 grams of sucrose, and 1 mole of sucrose is 342.30. So moles of sucrose, or grams of sucrose cancel out, and we end up with 0.04996 moles. Well, now that we have moles, we can figure out molality. We're going to go ahead and to figure out molality, take the moles of sucrose, divide by kilograms of water. And they gave us grams, but remember at this point, pretty easy, just move that decimal place over 3 times. So take the moles we just calculated, divide by 0.2 kilograms, and the molality is 0.249 molal of sucrose. Alright, so we have M, we have Kf, and we have I. We can plug it all in to find the delta Tf. So here we go. There's the Van't Hoff factor of 1, our Kf of 1.86, our molality of 0.249, and we see we get a change in the freezing point of 0.465 degrees Celsius. So that's a change in freezing point, but they want to know what the actual freezing point of this is. Now water, it's pretty easy. This is all the same stuff. Our new freezing point, water freezes at 0. So all you have to do is take 0 minus your change in freezing point. Now why is it a subtraction? Well, remember, we are depressing the freezing point, so it's got to go down, i.e. negative. Now, since it's a 0, it's super duper easy. The actual new freezing point is just negative 0.465 degrees Celsius. So that's how you would do it. Just make sure you have moles, calculate molality, make sure you have I, you look up Kf, and then just plug it in. Let's do one more problem. Now, it's not in your notes packet. I just added this in. If you want to go ahead and put it into on your notes, that's totally fine. So here we're starting off with a new problem. And I already pulled out the information. What is the new freezing point for a solution that contains 65 grams of sodium sulfate dissolved in 500 milliliters of water? Mass of the solute, 65. Mass of the water, 500 grams. Now, how did I know it was 500 grams? Well, remember, first semester we learned 1 mil is equal to 1 gram, so 500 mils is 500 grams. Van't Hoff factor of 3, because there's 2 sodium ions that will break off, and 1 sulfate, total of 3 ions, so Van't Hoff of 3. Kf is still 1.86 because we are dissolving it in water. And then molar mass of sucrose is not given, but easy to find, 142.04. Do the same thing we did in the previous problem. Let's find moles, molality, delta T, and then the final freezing point. So 65 grams of sodium sulfate. 1 mole is 142.04 grams. You end up with 0.458 moles of sodium sulfate. Easy peasy. We've been doing that for months. Now go ahead and take those moles and find the molality by dividing by, your mass in kilograms. So make sure you move that decimal place over 3 times. 0.5000 kilograms. We'll end up with a molality of 0.915 molal. And then go ahead and plug that into your delta Tf equation. So there's our I of 3, our Kb of 1.86, and our molality we just figured out. This is getting a much bigger shift in the freezing point, because one of the reasons is because our our Van't Hoff factor is 3 rather than 1. So that's huge. Alrighty, so now we have the change in the freezing point. Let's go ahead and find the final freezing point. Again, it's water, so it's easy peasy. 0 minus our change in freezing point. Easy. So it's just going to be negative 5.11 degrees Celsius right here. That's it. Easy peasy once you get the hang of it. Just takes a little bit of practice. The end.